I believe that I was on this slide. So in a paper that we published in May of this year, we recover sensitivity to treatment as a probability distribution. So my goal for this slide is to convince you that that is a worthwhile effort and that sensitivity to treatment is in and of itself an important parameter when modeling. I think this is the case because in a lot of cases, if you have something like prostate cancer, you have PSA data. In other cancers, maybe you have similar biomarkers, and you just get a measurement of that biomarker over time. Any other data involving the composition of the tumor is going to be expensive and difficult to obtain. So if you can use just tumor volume data to learn about the tumor composition via sensitivity to treatment, that's a really strong and exciting outcome. Then why would we model sensitivity to treatment as a probability distribution? Well, that's going to be because number one, you don't necessarily have to assume a number of subpopulations in the tumor. You can deal with mutation, you can deal with plasticity. All of this could be encompassed by a sensitivity distribution rather than a scalar. And mathematically, distributions are just more nuanced than scalars. So for the purposes of this talk, I have a sensitivity distribution as a sample on the right. 0 to 0.5 is going to indicate more resistance, and 0.5 to 1 is going to indicate more sensitivity. The proportion of population is what you see on the y-axis. If you are interested in this work, all of the code is in my GitHub. So here's the model in a nutshell. I will not go into the equations. What you need to know is that it is pretty chill. We start with a known distribution, which is the middle figure, the distribution in red. This is kind of a by Gaussian for this example. We use that distribution to deliver synthetic tumor volume data. So those are the data points that you see on the left. Then in the inverse problem, we fit to just that data, and what it spits out is a probability distribution that is inferred. So the blue dashed lines in the middle figure are the inferred probability distribution. And this is a very sort of easy, noiseless case, but you can see that both to the data and to the PDF, we get really strong fits. And that is super encouraging. Finally, I'll just mention, because I'm a mathematician, it is important to the theory of this that we infer a CDF that corresponds to the recovered PMF. That does not matter to a patient. So to do this all with synthetic data, we danced with a number of different data points, going from as low as 6 to as high as 100. We explored different levels of proportional noise. We used a bunch of different underlying distributions, including both continuous and discrete options. And finally, I mentioned we don't have to know a priori a number of nodes in the mesh for the distribution. That's just because we're using AIC in this case. We can also just use lowest error. They both tell the story pretty clearly. So we succeeded with synthetic data. Now it is time to discuss what happens with in vitro data. So there is an extremely super cool paper called Phenopop that provides the data whose information is in the box. What you need to know is that we have cells that have been appropriately mutated to be resistant and sensitive to treatment under 11 different dosages in different dishes. So that's the figure that you see on the left are these resistant cells. And you can see I put resistant with a question mark because they're responding differently to the treatment, even though in theory, these are all batches of similarly resistant cells. And what we recover when we perform the inverse problem on this data is primarily S equals 0 value. So we take in data that we know to be mostly resistant, and what the inverse problem spits out is the information that this data is mostly resistant. So that is an exciting and good result for us. Next, we explore what happens in the sensitive cells. Sensitive gets 2 question marks because it is even more clearly responding to the dosage when we wouldn't necessarily expect it to. Correspondingly, the PMFs that we recover get mostly S values, sensitivity values, of greater than or equal to 0.5. So the mostly sensitive data appropriately recovered as sensitive, varyingly sensitive. Finally, this data set gives us a bunch of different proportions, different mixtures of the sensitive and resistant cells. And unsurprisingly, we get a mixture out of the mixture data. So finally, one of the reasons that I'm referring to this as the exponential model, the exponential growth model, is that we explored a number of different growth terms and settled on a very simple exponential growth option for the growth term. And one of the reasons we did so is that we are able to recover net growth rate through this model. Now, the PhenoPop paper, the same one that gave us the data in the previous slide, was able to compute their version of a net growth rate using their model. So when we computed our net growth rate, we found that they matched really closely. And this is incredibly validating to how we're recovering sensitivity and the setup of the model we have right now. We had some doubts when we were kind of going through the data if our results were appropriate, and this kind of really validated those results. There's only one exclamation point after our net growth rate. I can tell you there were a lot more exclamation points in the Slack when I sent off this figure. Okay, so the big research question then today is, can we simulate treatment schedules over multiple cycles? And can we do that and select like an optimal strategy, right? So here I have 2 simulated treatment schedules. They go over about 6 cycles each. You have on-treatment periods, off-treatment periods, and the only difference between these two is these schedules. So same initial distribution, same growth and death rates, everything. What you see is that the blue data decreases and then eventually starts to come up a little bit. The red seems to explode a lot more, but with each treatment cycle, you can see that it is still responsive to treatment, right? Like at the start of each treatment cycle, it is getting brought down. So if you were a clinician making an educated guess about how to treat a patient based off of just this information, you might trend towards the blue because the blue is still below the initial condition. But let's explore what happens if we look at the parameter sensitivity to treatment. Okay, so this is what we get for the blue schedule. The first treatment cycle is on top, all the way down to the one on the bottom, and the blue is getting darker as sensitivity gets worse. And what we see is that it crosses the threshold from sensitive to resistant at like the 5th cycle. So that's the arrows you see. And if you follow that arrow to the treatment schedules on the right, you can see that after that arrow, where it starts creeping up even during treatment. So the sensitivity is really helping us tell this story. Meanwhile, if we look at the red, there's no crossover yet. It stays in that sensitive zone. It gets less sensitive, but it's still sensitive. It's still more sensitive to treatment than not. And that makes sense as well, because for each cycle of treatment, it is still decreasing with the dosage. So this is cool. This is 6 cycles. Can we use this to predict what would happen after a few more? Yes, we can. Otherwise, why would I be asking that question? So if I take it to about 10 cycles, I'm going to tell you about day 158 for both of these hypothetical tumors. It actually so happens that the Schedule 1 tumor volume blows up, and it becomes over 1.4 times the size of the red tumor. And conversely, they both actually come to the same exact sensitivity value. So what you might have assessed or recommended based on just the tumor volume actually becomes very different if you use the sensitivity to indicate and predict what's going to happen going forward. So knowing that at day 158, we actually have an extremely blown up, much larger blue tumor down the road might help us make better, more informed decisions for this hypothetical patient. So we have some exciting next steps in this project. One is to make a turn towards adaptive therapy and model turning on treatment when a tumor volume threshold is reached or other forms of adaptive therapy. Next, we have this balance to look at between lower tumor volume and higher sensitivity. How can we find a way to perhaps quantify that balance? And finally, we have access to a rich source of patient PSA data. And so I look forward to going through the emotional throes of trying to fit that. A big thank you to the Router Lab at UC Merced, to my funding, the organizers. If there is one thing scarier than the ghosts and the ghouls and all that this Halloween, it is the job market. So I would like to announce that I am finishing my PhD and I'm looking for postdocs. My CV is on the pumpkin. My other information is here, and I will also be here next week at the workshop. Thank you.